in your calculations, right? Also, make sure you're paying attention to the question that's asked, right? So for example, you might try to go from moles of Cl2 to moles of, say, CCl4, but that's not the question it's asking. It's asking you for grams of CS2. So always make sure you're spending the time with the question to underline things, to circle things, you know, what are you looking for? So many students just rush right into an answer, but it's worth a minute of your time to really read the question and make sure you're doing what they're asking you to do. So I'm just going to peek through some of y'all's responses real quick. 0.310, 0.3098. So far, so good, right? So those two answers seem close. 7.862. 7.86. So y'all are getting similar answers. I don't know if you're right or not. Now here's one that says 0.31. So let's take a moment, because some of y'all are getting different significant figures. So let's talk about significant figures for a second, just making sure we know what we're doing. So 25.0 liters, that is 3 sig figs. 120 degrees Celsius, once you do the math, is 393 Kelvin. That's 3 significant figures. The pressure is 0.40. That's 2 significant figures. So if we're worried about significant figures, and if you're just used to doing it, maybe our answer for part A, subpart I, maybe the answer should just be 2 significant figures based on the 0.40 atmospheres. Let's see what else y'all got. 0.31, 7.9, 0.30, 7.9. Oh, this is some great work. Look at this student. PV equals nRT. They rearranged it, found the number of moles of 0.31. All right, so y'all seem to be getting about the same answer. All right, so far so great. Okay, that's great. We'll show you the answer here in a little bit. So that was part A. Let's look at what the next part would have been. All right, at 30 degrees, the reaction is thermodynamically favorable. Now, for some of you, you may not have seen that term yet. Maybe you're just now starting Unit 9, totally okay. Thermodynamically favorable means the reaction should happen if you get the activation energy taken care of. So you've done kinetics. So if you can get to the activation energy, thermodynamically favorable, nature says, yes, I want this to happen. It should happen, right? At 30 degrees, it's favorable, but you don't see it. At 120 degrees, the reaction occurs at an observable rate. So cold, you don't see it. Warm, you do see it. Okay. Explain how the high temperature affects the collisions between the reactant molecules so that the reaction occurs when it's hotter. How does high temperature affect collisions? Okay, that's one thought. And then it says the graph below shows a distribution of energies of molecules when it's hot, 120 degrees. Draw the curve, so draw on the graph, that shows the distribution for the energies. So that's what it looks like at 120 degrees. They want you to draw what it looks like at 30 degrees. Okay, well both those tasks seem possible. So let's review what we know. We know that in subpart I, hotter means faster, right? So hotter molecules move faster. So how does that affect collisions? Well, we know that hotter means faster, means more collisions, and not only more collisions, not only are they going to run into each other more, they're also going to run into each other with more energy. So we know for a chemical reaction to happen, they have to collide. That's the first part. They have to run into each other with enough energy, right? And in the correct orientation. So I think for that first part, it's going to be important that we talk about higher temperature means more collisions, right? They're hitting each other more often, and also that they run into each other with more energy, right? Because faster molecules come from hotter molecules. The second part, colder is slower. All right, so at 120 degrees, that's our graph, and we want to draw the colder molecules. So for y'all, for this slide on Pear Deck, I want you to go ahead and draw right on top of the slide, right on top of the graph. What do you think the line would look like if it was a cooler set of conditions, 30 degrees, not 120 degrees? Just go ahead and take a stab. What do you think this would be? Last week it was cold outside and I actually had tea. This week it's warm outside and I'm having water. You'll also notice I'm rocking a Viking hat kind of a thing. So hopefully you enjoy that. You'll notice Mr. Poe is rocking an Auburn hat, which I can't agree with, but he put it on specially. So I appreciate that. He needs an Auburn hat though with pigtails coming down. I think that would be nice. You need some of those. So far in this question, the first part seemed pretty easy. The second part, this doesn't seem bad. I think that subpart I, that's got to be kinetics, right? And this part, I think, is also kinetics because it mentions that activation energy thing. So this looks like an awful lot of all the free response questions. I think that these are like a potluck or like a casserole, a mixture of a bunch of stuff. Oh, Miss Jennifer is wearing a Alabama hat. Is that what that says? Okay, all right. You're very small on my screen, so I was trying to figure it out. All right, I'm just going to peek at some of your answers real quick. All right, there's a graph. Okay, lovely blue color, by the way, whoever chose that. Oh, see, all right, good. All right. Oh, I think some of y'all have seen this question before. All right. Cool. All right, so that's a lovely graph, red and pink. That's lovely. All right. So one thing for y'all to know about these graphs, the y-axis is basically telling you how many molecules there are, right? So that peak in the middle of the graph kind of tells you, well, that is the average. So the hump right there tells you that's the average speed, the average energy of collision. So the area under the curve, so think about that whole hill they drew, represents all of the molecules. So when you draw one cooler, you want to make sure that the area under the curve is approximately the same. So your curve, think about the area under the curve being like a volume, right? Like a volume of a something. And so you want to make sure that volume, the number of particles or the number of collisions is the same. So as y'all do that, be thinking about that. And if you get this wrong, totally okay. I saw some right ones and some wrong ones because we're going to tell you how to make it right. All right, so that was part B. So we did part A, we did part B. All right, let's see. C. Oh, this is just like 2 weeks ago. Okay. Complete the Lewis dot diagram for S2Cl2. Now, y'all, I don't have to tell you how to do a Lewis dot diagram. If you see one of those, knock it out. But I will help you calculate a little bit just in case you don't have a periodic table in front of you. So chlorine has 7 valence electrons. There's 2 chlorines, each with 7 valence electrons. So that's a total of 14 valence electrons. And sulfur is right underneath oxygen. So sulfur has 6 valence electrons, and there's 2 of those. So total valence electrons would be 7 plus 6 plus 6 plus 7. So that's 12 and 14. I'm getting something like 26. So when you're drawing your Lewis structures, be thinking about, I need to draw 26 electrons in there somewhere. For the second part, they would like to know what's the approximate value of the bond angle. Now, here's what I want you to think about. After you draw the Lewis structure, which I know you're doing now because you can't wait, but listen to me anyway. As you're drawing the Lewis structure, don't think, oh, chlorine, sulfur, sulfur, chlorine is all in one line. Don't think it's, oh, this is exactly how it is. It must be like 180 degrees because that's what it looks like on the paper. What I want you to think about is, okay, now that you have your Lewis structure, I want you to think about, okay, what shape is that? And your shape could be bent, right? That was a possibility. There was trigonal planar. That was one possibility. There was trigonal pyramidal. That's a possibility. There was tetrahedral, right? So be thinking about, based on how you do the structure, think about what that bond angle might be. And you can just draw the number. So if you think the number is, I don't know, 120, then write 120 degrees or something like that on your answer. So far, this isn't bad. There's been a little bit of kinetics, a little bit of like gas law, stoichiometry. That's been okay. And Lewis structures, and hopefully you've done some of this. So far, so good. It's not too bad. I just realized I have a bad shadow on my face. Let me turn on the light. That way y'all can see my pigtails and all their, not pigtails. Yeah, pigtails, sure. In all their glory. All right. Oh, this is great, y'all. We got 35 people on Pear Deck and 24 of y'all have already answered. I'm just going to start to peek, see what we got. All right. Good Lewis structure. We don't have a bond angle yet, but all right. There's a Lewis structure. There's a Lewis structure. Okay, somebody said 109.5. Sound like a radio station. 107. Okay. All right. 10. I know you're still right. 109. All right, good. You know, the best news is all of y'all are getting the same Lewis structure so far. So that's either good news or bad news. It means we're all right or we're all wrong. So we're at 109, a little bit less than 120. Oh, I love this. It's got dots according to each one. Now, here's the reminder. When you're trying to show bonds between things, probably better to use a straight line. It's okay that you throw the electron dots in there, but probably better to show, hey, this is a bonding pair by showing like a single line, if that's what you're trying to do. So I'm getting like, ooh, here's a 105. I got a lot of 109s. Ooh, there's a double bond. That's exciting. So remember the goal, for those of you still working on your Lewis structure, the goal is for everybody to get 8 electrons. And by spending your 26 valence electrons and rearranging them kind of so that everybody sees 8. So make sure every element, the chlorines and sulfurs, each has 8. There's 108, 109.5. All right, there's another double bond. So far, so good. All right, so far, so good. All right, y'all are doing tremendously for a Thursday night, 2 weeks out before the AP exam. All right, great job, everybody. Okay, great. All right, so y'all can totally crush Lewis structures. That's great. All right, let's see. That was part C. So let's keep going. Part D. I know what you're thinking, like, how long can this go on? A long time. This is a 10-point question. It can go on a very long time. All right, let's see. CCl4, that was before. I know there was a CCl4. Can be produced by reacting this with this. Okay, there's a chemical equation. All right, maybe I'll need that. Let's see. At the completion of it, a chemist separates the CCl4 from the HCl. So they're both products. we separate the CCl4 from the HCl by cooling it to 70 degrees. So let's see, we started at 400, we cooled it to 70, at which temperature the CCl4 condenses. Okay, so that condense is a gas turning to a liquid. So CCl4 turns to a liquid and the HCl is still a gas. Okay. Identify all types of intermolecular forces in HCl liquid. Okay. So I need to remember what my intermolecular forces are. Okay, I'll do that in a second. What can be inferred about the relative strengths? So relative strengths, you need to make sure you say this molecule has stronger intermolecular forces than that molecule. Don't say something like they're stronger without telling me which one you're talking about. So that's a good way to not earn a point. So make sure you're telling me the HCl ones are stronger than the CCl4 or the CCl4 are stronger than HCl. You don't have to give a number, right? It's relative strength. So this one's stronger than that one. Justify your answer in terms of the information above. So let's see, what do we remember about intermolecular forces? So these are the ones I remembered earlier today when I was doing this. So hydrogen bond seems like it's always the answer, but sometimes it's not. There's dipole-dipole, LDFs, ion dipole, dipole-induced dipole. Now, let's remember what those are real quick. So H bonds are a hydrogen stuck to F over N that's attracted to F over N on another molecule. And that's a hydrogen bond. Dipole-dipole just means a polar molecule attracted to another polar molecule. LDFs are for anything that has electrons. So if you have electrons, you have LDFs. Ion dipole talks about when something that's an ion, like sodium ion, is attracted to something polar like water. And dipole-induced dipole, I remember the name, but I don't know what it means. That's a good thought, right? Then for part two, I just know that a higher intermolecular force, a stronger intermolecular force, means a higher boiling point. And the one that condenses first is the lowest boiling point. So whoever condenses first has the lowest boiling point because it turns to a liquid first. The other one is still a gas, right? So the one that condenses is kind of like undoing boiling. So it's got the lower boiling point. So based on that, go ahead and answer the question in Pear Deck. Go ahead and identify. Now, keep in mind, what does identify mean? Write them down and you're done. You don't have to say, the types of intermolecular forces present in HCl liquid are. I mean, if you did, that's fine. It's not necessary. You can totally just say, it's this and this and this and this, just write them down and you're done. This is the beauty of identifying. For part two, make sure you justify your answers and that means claim, evidence, reasoning. Your claim is this one has stronger intermolecular forces than that one. That's your claim, right? So you're going to write that. Your evidence is going to be that information they gave you about which one condensed. And then your reasoning is going to be something that shows that you understand how the strength of intermolecular forces connects to boiling points. So go ahead and take a moment and answer the question. I think this one I could have done in just regular chemistry class because we talked an awful lot about intermolecular forces. So far, there's not a ton of like that scary stuff from AP, like, ooh, acid base, lordy, that's hard. Sometimes like some of that thermodynamic stuff, delta G and delta S, that kind of thing can be kind of hard. But this so far, it seems right up my alley. I think I could totally earn a bunch of points on this. Oh, y'all are doing great, by the way. This is 24 answers. I know I like to talk a lot, and that's part of my charm, but y'all are answering great. This is great answers so far. I'm just going to start to peek at them to see what we're doing, okay? London dispersion, dipole. CCl4 is stronger than HCl. Dipole, and LDFs. LDFs, hydrogen bonding, or an ion dipole. So keep in mind that ion dipole, you have to have an ion somewhere, right? So ion dipole would be something that's polar, like HCl. I'm with you there. HCl is polar. But you'd also have to have some ion present. I don't really see that in this one. And remember that hydrogen bonding, hydrogen has to be stuck to fluorine, oxygen, or nitrogen, F or N, in order to make a hydrogen bond. So keep that in mind. LDF and dipole. So if you said dipole, remember dipole is not an intermolecular force, but dipole is. So dipole means polar, and dipole means a polar molecule attracted to another polar molecule. Dipole, and LDFs and dipole. All right, y'all are doing great. Y'all are doing great. I don't even know why we're doing this review session. Seems like y'all totally did. I know, we can always get better, right? We're fine. All right. All right, so far so good. Okay, now I'm going to show y'all the answers in a little bit, and I want y'all to keep in track what your answers were, right? I want you to be thinking about how you answered the questions, right? And from that, you're going to tell me kind of what you thought your score was. And remember, on this, no one knows who you are. So Jason or Peyton or Jonah or Sia or Eubine, I can't tell which answer belongs to you. So feel free to answer honestly. No, there's no judgment here. All right. So several of you are saying hydrogen bonds, and there is no F or N. So you got to remember, you got to have F or N in the molecule somewhere to have those hydrogen bonds. All right. So we've answered A, that was stoichiometry and PV equals nRT. We answered B, which was like kinetic stuff. We answered C, which was, what was that? Lewis structures and bond angles. And then D was all about intermolecular forces. So is it over? Is the question finally done? Or does it just keep going? Turns out it's done. So we only went through part D. Praise Jesus. All right. So how did you get the points? So I want you to go ahead and keep track of how many points you get here in a little bit. Right. So just like we said, the first one is PV equals nRT. So we plugged in 0.4. We plugged in 25 liters. That was given to us in the problem. We plug in the R value, 0.08206. That's right from that reference sheet, right? And we had to remember to change our temperature in Celsius to a temperature in Kelvin. So you get 1 point for finding the answer 0.31. Now, if you entered 0.3099, I know a couple of y'all did that, you're not going to lose the point for sig figs here, because the sig fig question, I think, is in a later one, so don't stress. But always be thinking about, am I putting this in the right sig figs? That's an easy thing to do. And then you had to take your answer. Now, here's my point. For part A, subpart II, y'all don't need to have my answer. You need to have an answer that corresponds with the answer you got. So let's say you thought the answer was 0.5 moles of Cl2. As long as you use that answer in part II and did it correctly, you could totally get the point, that second and third point, even though you screwed up subpart I, right? So just keep that in mind. So the reason why it's 1 mole of CS2 to 3 moles of Cl2, that came from the balanced equation. And then the 76.13, that comes from molar mass from the periodic table. So carbon is about 12, sulfur is about 32. So 12 plus 32 plus 32 comes in somewhere close to 76. All right, so wow, you get 2 points just for doing some stoichiometry. So I want y'all to realize that in a 10-point question, you get 3 points, 3 points just for doing stuff you learned in regular chemistry. So PV equals nRT, and 2 points for doing the stoichiometry. So 1 point for the mole ratio. So as long as you put 1 to 3, you get a point there. And then you get 1 point for the answer that you got that corresponds to the answer above. So most of y'all got 7.9 grams. That's great. But if you happen to put in a different number of moles to begin with, as long as you did the math right and it kind of set up like that, then you would get the points for subpart II. So that's great. Those of you who aren't joining in the Pear Deck, you're missing out on some fun. So go ahead and join the Pear Deck. It's free, right? Unless you'd like to pay me some money, I'll give you my Venmo account later. We'll see how that works. All right, so that was part A. 3 points, 3 points. All right, good. So for part B, what did you have to do to earn that point about collisions? All right. They have a greater average kinetic energy than the lower temperature. There are more collisions with sufficient energy to overcome the activation energy. So they have a greater average kinetic energy. Okay, we said that they're faster, right? And so there'd be more collisions. But what we didn't say, and this is probably where I would lose the point, I said there are more collisions and they're more with energy. But the part I missed, and this is something I can fix, right? I can get better by the time the AP exam comes along, is I really needed to talk about overcoming the activation energy. And the reason why they want you to talk about the activation energy is, remember in the question, they said, hey, at 120 degrees, you see it happen, but at 30 degrees, you don't see it happen. So in order to get that point, you have to talk about there are more collisions and that they have enough energy to overcome the activation energy. So a lot of y'all probably didn't get that point. That's totally okay. You're going to miss some points. But think about what did you have to add to it to do just a little bit better. And if you had just said, yeah, it's got more energy to overcome the activation energy, boom, you'd get that point. Notice in the graph needs to be basically a curve that is higher than the existing curve. So the dotted line shows a curve higher than the curve you started off. So you got to have, your curve has to have a peak that is higher than the original curve and to the left. So as long as the peak was higher and to the left, you got 1 point. And then you had to include that the graph doesn't just die before it gets to the activation energy line. You had to include that the graph continues past the activation energy, but is lower than the original curve. So as long as you had your curve lower than the original curve, and it still ends past the activation energy line, you would get that second point. So when we're talking about these curves, here's what I want you to think about. When things get cooler, I want you to put your right hand up, and I want you to imagine squeezing that graph from right to left. So I want you to imagine when it gets colder, squeezing that graph. So squishing that graph over, and that graph will get taller and kind of move off to the left. By the same token, if you make it warmer, I want you to imagine putting your hand on top of it and kind of pushing down. And so when things get hotter, the graph will spread out some and be lower than the original graph. But all of a sudden realize, here's what I want y'all to realize. Part A and B, total of 6 points. 6 points just in part A and B. So this is pretty good so far. All right, let's see. Part C. Oh, C diagram above. Y'all totally crushed this. Most of y'all crushed this Lewis diagram. So if this is what you got a point for the correct one. Now, those of you who didn't draw lines between them, that's okay. Because you show the electrons between them, they understand that you mean like a bond, but maybe you want to draw that bond in next time. So you get 1 point just for that. So now we're up to 7 points. And then you get 1 point for saying anything between 104 and 110, right? So if you just wrote 104, you wouldn't get the point. Because see how it says between 104 and 110? That means it can include 110, I mean 104, and it can't include 110. So as long as your answer was somewhere in between there, then you would get that point. And so let's think about why is that? Well, typically for 4 areas of electrons, we would say that's like a tetrahedral electron shape. And you would guess that the bond is 109.5. But every time you have a lone pair of electrons, it kind of squeezes that bond a little bit more. So if you have one lone pair, instead of being 109.5, maybe it's like 107. It'll squeeze it a little bit. And if you have 2 lone pairs, then it would squeeze it a little bit more. So it's probably going to be more like 105 or 104.5. So as long as you put down something that's between 104 and 110, you earn that point. All right, so we're up to 8 so far. So this isn't bad. All right. All right. For some reason, it's not, there it goes. Okay. All right. Then the last part, identify all the types of intermolecular forces. Yeah, identify all the types of intermolecular forces. So if you said dipole-dipole and London dispersion, then you got a point. But it could only be those 2. So if you wrote H bonds, you can't have H bonds without F or N, you wouldn't earn that point. But realize that's 1 point out of 10. So maybe right before the exam, you go back and review your intermolecular forces. Very important. And then this next point was probably the hardest point to get, just because you have to kind of reason your way through. So CCl4 has to be stronger. And all you had to say was because CCl4 condenses at a higher temperature than HCl, right? So you're saying that CCl4 is stronger because it condenses at a higher temperature than HCl. Or you could have said that HCl condenses at a lower temperature than the CCl4, right? So some kind of reasoning like that. So that's 10 points. So what I want you to do on Pear Deck is go ahead and throw up a number. So somewhere between 1 and 10, how many points do you think you would have scored on this FRQ? So somewhere between 1 and 10. All right, so I'm just going to peek at y'all's answers. So we got everything from 2 to 10. Hey, if you got 10, good for you. And a little bit of in between. All right, so some of y'all did kind of low and some of y'all did really, really well. I'm saying if you're here tonight trying, I'm proud of you. But we need to get some of those like 2, 2.5, 3s. We need to get some of those up a little bit higher. So keep track of the things you did really well in and keep track of the things you need to work on and make sure you're working on those as we get closer to the AP exam. So in 2017, what was the average for this question? The average was, I looked it up just a little while ago. Hang on. 5.47. This was a pretty high average. So here's what I'm saying. If you scored 6 or above, you're on your way to a passing score because you're doing better than the average score in the AP exam. So if you did 6 or above, great. If you didn't quite get to 6, then think about those areas that you could improve in. All right. So that was number one. Here was another one that was a little rough. Number two was a little rough. Again, here's some Lewis structures, but they're giving you the Lewis structures this time. Explain why the diagram on the left is a better representation than the diagram on the right. Justify your choice based on formal charge. So hear that justify word again? Justify means claim, evidence, reasoning. The claim is already given to you. The diagram on the left is better than the one on the right. That's the claim, okay? So, oh man, what is formal charge? Well, it's been a while, right? It's been since like unit 2 since formal charge. So let's remember what that is. Formal charge is the number of valence electrons, not the E, the number of valence electrons minus the number of electrons that are in lone pairs minus half the bonding electrons. All right, so let's do formal charge together for that first molecule on the left. So carbon, if you look on the periodic table, carbon has 4 valence electrons. So it'd be 4 minus the number of electrons in lone pairs, which is 0 for carbon. For carbon, that's 0. So 4 minus 0 minus half the number of bonding pairs. Well, it sees a single bond and a triple bond, and each bond is 2 electrons. So a single bond and a triple bond is the same thing as saying 8 bonding electrons. And so let's see, half of 8 is 4. So number of valence electrons, 4, minus electrons in lone pairs, 0, minus bonding electrons would be 4. So 4 minus 0 minus 4 is 0. So the formal charge of carbon in that on that left-hand molecule is 0. So given that, y'all go ahead and think about and write your response now that you kind of remember. Oh, and one more thing. The goal is for formal charge of 0 for every element in the compound. That's a very general rule. There's some other rules, but it works for this one. Try to give everybody a formal charge of 0 for every element in the compound. So go ahead and write your response to that question. And Brody, I'm glad you love chemistry, man.
I thought you were talking to me and I was very confused.
Oh, sorry. Yeah. Brody, man, my bad.
Okay, I got it now.
Mr. Ballinger is like, all right, sure. Mr. Poe, I'm glad you love Auburn. Miss Jennifer, I'm glad you that you love Alabama.
I'm glad that you love bacon.
I do love some bacon. And Miss Jennifer, we went and ate at that Margarita Grill the other night, and I thought of you.
Woohoo!
It was delicious.
Great place to eat.
Mm-hmm. For those of you who haven't eaten dinner, I'm sorry to bring it up, but it was good. We had homemade guacamole. That was delicious. Well, not homemade, sorry. They made it right there at the table. That was delicious. And I had some chicken thing, and we had chips, of course, and some queso. It was delicious. And again, if you haven't eaten, well, I just made you hungrier, so sorry about that. I'm not really sorry, to be honest with you. All right, so let's see what we've got. 16 of 39 answers so far. So far, so good. I know it's been a while since you did formal charge, so I can tell y'all, if you don't do very well on this one, that's okay. But make a note, right? Write yourself a note. I need to go over formal charge before the AP exam, because formal charge isn't super tricky, but it is tricky when you haven't done it in a very long time. You're thinking like delta G, acid base, KSP, and sometimes you don't remember that stuff from a long time ago. If I should turn my hat this way. That's a good look too. It doesn't fit quite right. Maybe I should tuck my pigtails up in my hat. All right, so I'm just going to peek at some of your answers real quick. All right, 18. Let's see. N is +1, O is -1 on the left, carbon is -1, +1, and 0 on the right. Okay, that's pretty good. All right, so y'all are writing down formal charges. That's great. Y'all are writing down some great answers. All right, so some of y'all are getting -1s for things, and I know I told you the goal is for everybody to be 0. So what do you do when everybody can't be 0? So the goal is whoever is the most electronegative should get the negative formal charge. So if you've tried and tried and tried and you can't get everybody to be 0, at least if somebody has to be negative, make sure it's the element that's the most electronegative. And remember, electronegative goes up and to the right on the periodic table. Right. Yeah. The person who wrote the diagram on the left is a better representation, is that the formal charge for the left. Okay, you just can't throw words at a page and hope they stick. So remember, when it says justify with formal charges, you're going to have to write the formal charge of every single element in that compound, right? Sometimes they ask you about like oxidation numbers, base it on oxidation numbers. Make sure that you have assigned oxidation numbers in the equation, because you have to use that data to back up your answer. So justify your choice based on formal charge. Okay, so far so good. I mean, that one's a little tough, but let's see where that goes. B, using the Lewis electron dot diagrams, determine delta H. Okay, delta H. And they give you a bunch of bond energies. All right, good. So bond energies, what is bond? Bond energies has to do with, it's like bonds broken minus bonds formed, something like that. So we have to think about that. Okay. And then C, a student claims that delta S is close to 0. Okay, delta S, if you haven't seen delta S yet, totally okay, you still got time. Delta S is something we call entropy, and entropy is the amount of disorder in a system. And so we look at, like, are they solids or liquids or gases? And we also look at the number of molecules. So I included the equation up top for you guys to think about that. And then it says, what species is present in higher concentration at equilibrium at 298? Justify your answer in terms of thermodynamic favorability. Now, y'all, if you haven't heard delta G before, you can answer part D. It's okay. You'll get there. You'll get to delta G stuff. But so if you can't answer D, that's okay. But let's write down everything that we need to know to answer this question. So delta H for bond energy is all the bonds broken minus all the bonds formed. Okay, so far so good. Delta S is change in entropy or disorder. And then there's this equation. It's on your reference sheet. Delta G is equal to delta H minus T delta S. So T is temperature, right, times delta S. Whenever you calculate delta G and it's negative, that means it's thermodynamically favorable and the K is greater than 1. The products, isocyanic acid, is favored. So negative delta G means thermodynamically favorable, K is greater than 1, and the products are favored. A positive delta G is exactly the opposite. So a K less than 1 and the fulminic acid, the reactants, are favored. Okay, so keeping that in mind, go ahead and write your response. What I'm going to get you to do is not answer the whole part. I just want you to answer the part that you think you can do the best. So if you think you can do B best, do that. If you think you can do C best, just do that one. Or if you think you can do D, unfortunately, you're going to have to do both B and C to get there. So if you're the high achiever and you want to do D, then you're going to have to do all 3. But for right now, I'm okay with y'all just thinking about, well, I could either do B or C on Pear Deck. Yeah, remember, you're just answering one of them real quick. And remember, you would get a calculator for this. So those of you who are like, ooh, do I get a calculator? Remember, for the free response, you always get a calculator. I'm just going to peek at some of your answers. I know a lot of y'all still typing. Go ahead. All right. Somebody answered B. So they found delta H is negative 246. Negative 246. Negative 2. Okay, cool. Oh, and y'all are including units. How great is that? Because, you know, units are important. So just flipping through. Here's a couple of people that decided to do just the entropy part. All right. So a lot of y'all are answering the C part, and that's great. So a student claims, explain why it's accurate. So just realize that you don't have to say the student is right? A lot of times y'all have to do that on these. But when the question says, explain why the student's claim is accurate, they're saying, hey, by the way, this is true. So you don't have to say, I agree with it, kind of a thing, right? So just all you have to do is explain why this statement that delta S is close to 0. Okay. I'm going to peek at answers one more time. And y'all just remember that since it's a peer deck, y'all will get some takeaways published. And at the end of this, they'll get shared with you to your Google Drive, I believe is the way it works. And this is also being recorded, so you can also go back and look at it later. All right. A lot of y'all are answering C, and that's great, right? So, and a lot of y'all could do both B and C. That's great. So, and then part D, even if you couldn't get to part D, you've gotten the points that you can get, right? So, okay. All right. So let's just keep going. Ooh, lower D. This question just keeps going. The last one ended at D. All right. So explain how a student runs this reaction, blah. Here's some data and a graph. The student proposes that the rate law is rate times K times whatever that molecule is. Oh, urea. What urea? Oh, notice that for this one, the rate law has an exponent of 1 for the urea. And if it's 1, then that's first order, right? Because if it has an exponent of 1 in the rate law, then it's first order. Explain how the data supports the rate law. Using the proposed rate law in the student's results, determine the value of the rate constant K. Include units with your answer. Okay, so I have to find K with units. And then the student learns that the reaction was run in a pH of 13. Briefly describe an experiment, including the conditions that you would change and the data you would gather to determine whether the rate of the reaction depends on the concentration of OH minus. So, okay, so it was run at pH of 13, and you want to say whether it depends on the concentration of OH minus. So let's write down what we know. We've been doing this all along. For a first order reaction, we know that it's a constant half-life. That's just something you just know. We also know that from the reference sheet that the half-life for a first order reaction is T1/2 is equal to 0.693 over K seconds. So the half-life is equal to 0.693 over K. And this comes right from your reference sheet under kinetics, seconds, right? And the concentration of OH is tied to pH. I think pH has something to do with OH concentration. Seems like that's related. So it told me it was a pH of 13. So if we go back and look at the question real quick, what I want you to do is just look with me real quick because we're going to move on because I want to see one more. Explain how the data supports the student's proposed rate law. So find the first half-life. In other words, look at the data and figure out how long it takes for the concentration of the chemical to get cut in half. And when I look at the table, it takes 10 hours. So it goes from a concentration of 0.1 down to a concentration of 0.05, and that takes 10 hours. How long does it take for the next half to disappear? Well, we go from 0.05 down to 0.025, and it goes from 10 hours to 20 hours, which means it takes another 10 hours for another half to disappear. So the first half-life was 10 hours. The second half-life was 10 hours. That means the half-life was constant. And if the half-life is constant, that is a first order reaction, right? Notice it doesn't tell you it's first order. You have to get that from looking at the rate law. But because I bet you it's because the half-life is constant, right? And then let's just look at what some answers are, right? So here's the answer for that first part. The diagram on the left, carbon has a formal charge of 0. The oxygen has a formal charge of -1. In the diagram on the right, the carbon has a formal charge of -1, and the oxygen atom has a formal charge of 0. And remember what I said, who gets to be negative? It should be the more electronegative element, which oxygen is more electronegative. So if you just went through and assigned formal charges for each one of the diagrams, you got 1 point. And then you got 1 point for saying that oxygen gets to be -1 and not carbon, right? So you get 2 points there. All right, this is part B. This is that bond energy thing. So those of you who found bond energy, bonds broken minus bonds formed, then you get an answer of -246 kilojoules per mole. You get 1 point just for subtracting the bonds broken minus, bonds formed, you get 1 point for saying bonds broken minus bonds formed, and 1 point for the correct answer. So even if in doing the math, you were like, oh man, I can't math today. Even if you just showed the work of showing that it's bonds broken minus bonds formed, you would totally get the point there, and 1 point for the correct answer of -246 kilojoules per mole. Cool. All right, so that's 2 points there. So 2 points for A, 2 points for B. Let's look at C. There's no change in the phase. So we didn't go from a liquid to a solid or liquid or whatever. So it's a gas and a gas. And there's no difference in the number of molecules. So 1 molecule of gas becomes 1 molecule of gas. If you had just said that 1 molecule of gas becomes 1 molecule of gas, and therefore the entropy is about the same, boom, you get a point. And this last part I'll let you look at, but basically we want delta G to be negative. So if you had a value for delta H of -246 and delta S is pretty much 0, then that means that delta G is pretty much -246. So if you calculated delta G and said it's thermodynamically favorable, you get a point, right? And all right, sorry, if you said isocyanic acid, you get a point. And then you get 1 point for basically saying that delta G is negative, K is greater than 1. So if you said that, you get 2 points. So all of a sudden, y'all are starting to rack up points. If you didn't get one of the points, totally okay. Because remember, the goal is to get the most number of points you can. And then finally, if you had said that the half-life is constant, therefore it's first order, boom, you get a point. And then since we said the half-life was 10 hours, if you just take 10 hours and plug it into the equation that T1/2 is equal to 0.693 over K and solve for K, then you would have gotten the answer 0.069. Now that whole bottom equation, I've never seen anybody do that. If you love you some math and you wanted to do that, just realize that K comes from the integrated rate law for first order. But most people just plug it straight into the half-life thing. But make sure that you knew that it had to be the correct half-life of inverse hours. So you either could have written 0.069 over hours, or you could have written hours to the -1. Either one's okay, as long as you remembered units. So you had to have 0.069 and inverse hours. So if you don't remember doing that, and maybe that was pretty easy to do, but if you don't remember kinetics, maybe make yourself a note to go back and kind of look at first order, 0th order, second order, and how to find half-life. Right, and then this is the last part that basically says, what do I have to do? You just have to change the concentration of OH. That's all you had to say. So do it at a different pH. You could have said that. You could have done any number of things, but you had to say, change the concentration of OH, a different pH or something like that, and measure the concentration over time. So in other words, same thing you did before. So back in that original graph, it showed you how that stuff goes away over time, or how it grows over time, how it increases. Then you could have been like, oh, okay, yeah, just change the pH, different OH concentration, and boom, you get a point. All right, this is the last one I wanted to show you, make sure we got it in tonight. So this is one of the short ones, and this is Electrochem. And a lot of y'all maybe haven't seen Electrochem yet, but I just want to show you how easy this is. So this is one of the short ones. This is only going to be worth 4 points. So they give you what are called half reactions, and they give you the goal equations at the top. So see where it says dichromate is titrant. Okay, that's an equation that we're going to try and use, right? We're going to try to get to that equation. So in part A, subpart I, it says, what is the E for the reaction between CrO2, Cr2O7, and H2O2? What I want you to do is find the equations that have Cr2O7 and H2O2. And here's what I want you to remember. To find the E of the cell, you have to flip one of them. So they can't both be gaining electrons. One of them has to show oxidation, okay? So all you're going to do is figure out which one to flip. So look at the equation that says dichromate is titrant and figure out, do you want to flip the H2O2 equation or flip the Cr2O7 equation? And then once you decide which one to flip, when you flip the half reaction, you flip the sign. So if you flip the Cr2O7 one, so you flip it around so products become reactants, then you're going to make it negative 1.33, right? So go ahead and do that be thinking of that for those two, like which one would you flip for that first equation? And then same thing for the second equation, the cobalt ion, which reactions would you combine? You only have to combine 2 of them, right? So pick 2 from the table and then figure out if you need to flip any of them. And if you flip one of them, don't forget to change the sign. And then all you have to do is add them together, right? You just flip them and add them together, right? And then I just wanted you to see that the E for a galvanic cell is positive, and an E for electrolytic cell is negative. Some of y'all haven't heard those words before. That's okay. All right. So based on the calculated values, you have to pick the one that is thermodynamically favorable. which one would you choose? Explain your reasoning, and then calculate delta G. Well, this goes back to what I was saying before. A galvanic cell is like a battery. So a galvanic cell is something that happens, just like your cell phone working. It's just something that happens kind of on its own, thermodynamically favorable. So when it says, which one would you, which titrant would you choose for something that's thermodynamically favorable, you have to find which equation, the dichromate as titrant or cobalt as titrant, gives you a positive E, right? So go ahead and spend the last couple minutes we have. See if you can find E for that first equation and E for the second equation. And I'm going to actually have y'all record your answers. Sorry. I'm not going to have y'all record your answers because I screwed that up. So. And as y'all are working, let me just remind you that that last one we did, that was a little bit tougher than the first one we did. But that last one we did, its average was like 3.1, something like that. So on that last one that we did, if you guys got 4 points, 5 points, you guys did great. You're totally killing it. Doesn't mean you still can't learn some more and do a little bit better, but the goal is to do better than average. So on that one, you know, the average was 3. It's much lower than that first one we did. And the average on this one, I'm sorry to say, the average on this one, number 7, is 1.4 out of 4. So this is one of those short questions, and the average was 1.4. So if you can get 2 points here, 3 points here, you're killing it, right? And for those of you working, if you need an equation for finding delta G, because that was the second part, find delta G. Wow, this is not working. Hang on. There it goes. Calculate delta G in kilojoules per mole. If you look on your reference sheet, there's a equation that says delta G is equal to negative N Fe. So if you want to try calculating delta G, you can do that. Just it's negative NFE. Find the equation, plug and chug. So I know y'all are still working. Let me go ahead and go over what the math looked like. So for that first one, you kept the 1.33, and then you flipped the sign of the 0.7. So that first one was 0.63. The second one, you kept the 1.77, and you flipped the 1.84. And remember, this is recorded, so you can go back and look at it again. You can also just Google 2017 FRQ, and that'll take you back to those questions as well. But you get 1 point for solving both of those. So even if y'all just knew how to flip so that you can solve things, and this is pretty easy, boom, boom, 2 points. Now you have just done better than the average on the AP exam in 2017. All right, and then the last part, how do you do the very last part? Well, you pick the one that's positive. So since the dichromate one was positive, then you say, oh, that's thermodynamically favorable, right? So you just had to say that positive E is thermodynamically favorable. And then that last part, most all of y'all could have done. The tricky part, there were 2 tricky parts to part II. One is N, the number of moles. And if you go back and look at the half reactions, the number of moles of electrons that were transferred was 6. And so a lot of people are not real sure, what do I plug in for N, right? So if you go back to the half reactions and look at the values for the dichromate, see how it's 6 electrons? That's why you put a 6 in. All right. And then the big thing here is you got to get the units right, in kilojoules per mole. And if you just did the math, plugged in the math and did all the math and yay, then you would have gotten the answer 360,000. You have to remember to change the joules that come from volts to kilojoules by dividing by 1,000. So a volt, the 0.63 volts is joules per coulomb. And you just have to remember to change that to kilojoules. That was another way that people didn't quite get that point. All right. Thank you guys so much for coming out tonight. I'll be happy to stick around for another minute and answer any questions you guys have. And I'll go ahead and end this. We appreciate you, and we'll be back next week, right? No, not next week.
Next week is the regular study
Right.
session. Let me check the date, Danny. Hold on just a second.
Right, not next week. What am I thinking? That's not right at all.
Give me just a second. I'll tell you.
Okay.
So April 28th at 7 o'clock.
April 28th. Woo!
Yep. We had a pretty good crowd again tonight, somewhere around 60.
Yay!
That was good.
There you go. Thank y'all for coming out tonight, and y'all have a lovely evening. And if you didn't eat yet,